We would now like to use Maxwell's equations to show that energy conservation really holds if we define our Poynting vector this way. This is a beautiful example of the application of Maxwell's equations. It's a tricky calculation. Well, let's call it an advanced calculation. So let's begin with the relevant Maxwell's equations that we're going to use. So we have the Maxwell ampere law that the curl of the magnetic field is equal to mu naught times the current density plus mu naught epsilon naught, the rate of change of the electric field. And our other Maxwell equation that we're going to use is the Faraday law. The curl of E is equal to minus d by dt of B. And let's begin by looking at this term J. What will happen here is we're going to substitute J using Maxwell's equations, and then we'll use a vector identity that will enable us to actually cancel this term, and what we'll be left with after we use the divergence theorem is the equality with the Poynting vector. So notice that J is equal to the curl of B divided by mu naught minus epsilon naught dE dt. So if we substitute that into J, we have, and I'll just do the calculation, J dot E dV. I'm only going to write one integral. Well, that's always 3, but to make life easier, I might just have one integral. So when we substitute into J, we get the curl of B over mu naught dV dot E dV. And our next term is going to be negative. So we have minus epsilon naught integral of dE dt dot E dV. Now, notice right away, let's focus on this term. We can write this as minus epsilon naught. I'm going to take the time derivative out and write this as, in fact, I'm even going to keep the epsilon naught inside. So let's rewrite that as minus the integral with a d by dt on the outside of 1/2 epsilon naught E squared dV. Now remember, when you take a derivative, we have a vector identity here that d by dt, let's do this in partials, of E squared. This is d by dt of E dot E. And there's two terms if you take the product rule. And so what we get is dE dt dot E plus E dot dE dt. And those are identical. So that's twice E dot dE dt. And that accounts for the factor of 1/2, because over here we just have E dot dE dt, and the minus derivative gives us that. So this term represents the rate that the energy stored in the electric field is changing. Notice this was a plus sign, and we see right away, because of the minus sign, that's going to cancel the energy stored in the electric field. Now let's focus on this term. Our identity that we want to use is the following: that the divergence of a curl of two vectors is equal to the curl of E dot B minus E dot the curl of B. So notice that here is the curl of B dot E, but with a minus sign. So if we bring this term over to the opposite side, so we have the plus sign, I can now write J dot E dV. Now we have to be a little careful with signs. So I'm going to take this vector identity, I'm going to bring this term to the left, and the divergence to the right. And so I'll get it's equal to the curl of E dot B over mu naught. That represents this first term, dV. The second term is minus the divergence of E cross B over mu naught dV. And don't forget that we have this minus d by dt of U, energy stored in the electric field, dV, just to keep in mind that the energy stored in the electric field is 1/2 epsilon naught E squared. So far we've used the Maxwell ampere law, and we've used the vector identity. And now what we want to do is use Faraday's law with respect to the first term. So notice the minus sign. So I can write that as minus d by dt. Let's write, just keep things straight first, minus dB dt. There's Faraday's law. There's a 1 over mu naught dot B dV. And we now have minus, this is where our calculation gets a little bit long-winded, but we might as well keep these pieces in here, minus d by dt of the energy stored in the electric field dV. Now once again, we have the same type of argument that we had over here. We can write this first term as minus d by dt of 1 over 2 mu naught b squared dV. And right away, that is the energy density associated with a magnetic field. And we have the energy density associated with the electric field. And we have this extra piece, the divergence of, now I'm just going to use how we define the Poynting vector so that you see where it's coming in, divergence of S. So that is using Maxwell's equations and our vector identity to rewrite this term in terms of energy densities and fields. And now let's substitute with the minus sign, makes that one plus, makes this one plus, exactly canceling those two terms. And so what we see is S dot n hat dA. The energy densities are canceled. The only term left is the divergence of S dV. And this is true because that is the divergence theorem. And that's the third piece that we use in this, the fourth piece that we use in this argument, our vector identity, and finally the divergence theorem makes this true. So very complicated, but let's just summarize what we did. We want to find, we've claimed this vector E cross B over mu naught satisfies this equation. How do we prove that? We use Maxwell's equations. We start with this term, J dot E dV. We use the Maxwell ampere law to rewrite it. We've already seen the time derivative of the energy density showing up here. We have a curl of B over mu naught. This is where it's a little bit tricky using this fancy vector identity. So we've rewritten this term as a divergence and a curl. The curl of E is the Faraday law. And when we put that in, we see that that term represents the rate that the energy stored in the magnetic field is changing. We've already had the rate that the energy is stored in the electric field changing. And now we have this extra term in here. Notice there's the Poynting vector, but it's the divergence of the Poynting vector integrated over a volume. When we recast this equation, is it really true that this vector S through the closed surface is equal to these two terms? We've reduced these two terms to the divergence of S in the volume, and that's the divergence theorem makes the identity true. So using this equation for the Poynting vector is consistent with Maxwell's equations and energy conservation associated with electric and magnetic fields and work done by electric fields on charges.